Alright, so continuing what we were doing last time, we're going to look at some more programming using vectors and using transformations. To begin with, I'm going to show you one thing here in the desktop launcher. I added this here, config.x and y, just to be able to put the window in a specific place on the screen. I'm going to see how this looks now. Okay, let's just keep it there. That means if I'm only recording a smaller portion of the screen, this will at least land inside that. So what's happening here is we have this split view. We have two viewports. Each is one half of the screen. I'm just going to allow the left-hand side to stay there. We'll delete the other one and start from scratch with what we're going to be doing now. And then if we have time, I can embarrass some of the students by showing in the entire class their projects. Okay, so let's go in here. While I'm going through this, I'm going to try to kind of at least show every part of the program code. So if you're watching the video, you can pause anywhere and kind of write it up. But what we have now, let's just look at the core part here. We have the main game class, which we're looking at now. And it's still doing more or less the same thing as in the base project. We're just setting up the shaders here. We're more or less mainly setting up the shaders, setting up some variables for the shaders, setting thus. Then we're creating these static ways to draw simple forms, and what we're going to start by doing now is actually making a more complex form from all these simple forms using some transformations and then calling that as one function. So if we look at this, the rectangle graphic, we have the vertex buffer and we have this vertex pointer. We simply fill the vertex buffer here, and then we're basically, once we create it, we set it to a vertex pointer here. So the vertex pointer is simply a location in the shader that we know is going to be where the vertices are going to be read from, and the display function simply tell OpenGL which vertex buffer it should read from through this vertex pointer, and then it tells it which vertices, that is how many vertices and starting from where, and it should draw, and then which kind of base primitive it should use. Triangle fan here, line loop here. I'll look at the circle graphic as well, just to make sure everybody can have a nice place where this create function is. Otherwise it's more or less the same. We're just going through this loop with the cos and the sine, and then we're drawing it. Okay, so we have these basic forms as well as the coordinate frame graphic, which draws the little coordinate frame with two arrows. So our program currently still have to do this. Okay, so our program currently looks like this. Inside the main game class, we have the update function, which is simply allowing us to press certain keys and having certain things happen if they're pressed. And then it has some angle that's changing by some amount per frame, or actually some amount per second, since we're taking the time in here. And in the display function, we use that angle to spin things around. Just look at this here, setting up the viewport first, which is where on the screen we're going to be drawing, setting up the orthographic projection, which is which part of the world we're going to be projecting onto that viewport, and then we're setting colors and drawing stuff. This and this. And then the second part, I'm more or less gonna wipe that out and start over there. Let's just take this like so, and then we can start over from there. Okay, so the first thing that we're going to do now is we're going to make a specific class that holds a specific object, and that object should know how to update itself given input. Like we can tell it that it should be rotating to the left or rotating to the right or moving forward. It knows itself how it updates that. It knows its rotation speed, it knows its speed and acceleration. This object also knows how to draw itself, and it'll make a little bit more of a complicated display function using the primitives that we already have. So first things first, new class, and we'll call that class Spaceship. Yeah, don't really need anything else. So this spaceship needs a position, and at this point is a great time to actually kind of generalize our positions as well, rather than having to set these x position, y position variables all over the place. We'll make another new class. So we're going to make a few new classes here just in order to keep track of stuff. So we'll just call it point3D. Public float x. And this class simply holds x, y, and z variables. And I'm making them public so we can just access them straight. If you want, you can have them private and make get and set functions. A lot of the stuff we're going to be doing is done in a way where you can do it in a million different ways, as well as when we're accessing specific code or accessing specific functions. Do we make a static function, or do we make an instance function but a static instance that we talk to, or do we actually float instances around? It's up to you how you implement this. I'm going to implement it in some way here, just that that seems to fit what we're doing now. Yes?
Can I use a vec2?
The vec2 class, is it part of libgdx?
Yeah.
Yes, you can use that. That's cool. There are classes in, I think, Java util or Java math, also inside libgdx. You can use those vector classes if you want. The reason I'm making them from scratch is just because we're kind of going through what's happening inside them. So in the end, I'm going to make a vector class as well, and we're going to implement the dot product there, and we're going to implement moving the point by a vector, and so on and so forth. Just going to make whatever we need and try to put the math in a sensible location. So our spaceship needs a location. So point3D position. Okay, and I am going to make a display function here. Display, and then once we start making the functions, we'll see what stuff we're going to be needing in order to display. Do we need to access data? Do we need to access the main, what's it called, the main model matrix? And if we need to access the main model matrix, how do we access that? Do we get it handed to us as an instance? Do we talk to it statically? So we'll just decide that as we go. Okay, so this display function, and now I'm actually gonna just wait with this position and go into the main game class. And since we now have a display function, you can go in here and say, I'm going to make in the game class a spaceship that this game class can access. Private spaceship 1. We might add another one later on. And somewhere inside create, go ahead and say spaceship 1 spaceship. And finally, inside our display function, we're going to ignore this. Here we're setting up the right hand. We're setting up the right hand viewport. And now we kind of have to decide the size of the world that we're going to be drawing this spaceship in. I think something like from -50 to 50, so we have it 100 aside. That's something we can work with, and we'll just see what that does for the sizes of everything. Send it here and call spaceship1 display. Okay, we have an identity matrix here in the model matrix, so this should just draw the spaceship in the center of the screen. Right now, what's happening is, okay, that's still on the right hand side. We're looking at, no, on the left hand side, we're looking at the right hand side here. And now we just need to start drawing something for the spaceship. So I'm going to go ahead and say, just to set the spaceship somewhere, to forward frame graphic dot drop plot, just to see what that looks like, just to kind of get a handle on where we are here. Okay, if it's drawing anything, it's tiny. It shouldn't be that small though. So let's see what's going on. Take this code, set it in here instead of spaceship display. Drop plot. Okay, so yes, we're going to have to set the shader matrix here. Let's just do this after we set the viewport, like so, and see if that sets things straight. Okay, so now we have something there. That's fine. Now we're going to try to take it out again and call spaceship display instead, and see that this is happening inside our spaceship drawing function. Okay. So now we'd actually want that a little bit bigger. We want our spaceship to be a bit bigger. So either we're going to scale it inside the spaceship and just decide the base spaceship is bigger, or we could actually say we're going to draw the base spaceship in its own size, and instead go out here and say model matrix dot add scale. How much bigger is that going to need to be? 5, 5, 5. Like so. Let's see what happens now. So now I've simply scaled that up a bit. So we have something that we can work with. And to kind of make a little bit of a frame here. So at this point, we really need to start scaling these modules, these parts of the spaceship as well. So we really need access to the main model matrix that we have here. So either what we need to do is to say that the display function takes in some kind of main model matrix and we send that instance down. So that's one way to do it. Another way would be to make the main model matrix basically a static instance of model matrix that we can access from anywhere. So which version do you feel like works better for you? Do you understand the difference? One would be to go into just model matrix here and say I'm going to make one static model matrix. You can just call it main. And then we can access that from anywhere and just say this is going to be our main static model matrix. And any function and any class within our program can access that. The other way would be to do the same thing as we're doing now. That would mean that when we go into the game class, we'd have to change this here model matrix. We'd simply take that out and say, instead of having this class here, our game class would be accessing this static main model matrix class. Okay, that's one way. The other way would be to use this model matrix class, and every single display function that we call from there then needs to get that model matrix sent along with it so that it knows from where to kind of add, or onto what to add its own transformations. Which seems more sensible to you? Okay, so that means we have to make a bit more changes right now, but in the long run we can just access that from anywhere. So let's call this main here. Let's go ahead and take this matrix out. Then we'll have a bunch of places where we simply need to say model matrix, find model matrix, replace with model matrix dot main. Case sensitive, find wait, what? Place. Okay, whole word. Find place. Okay, so all of these things that we've been doing to this. Okay. Fine. So I'm hoping we probably have errors because this should be public. Okay, so no errors now, and our program runs. Okay, fine. So now wherever we are, we should be able to say model matrix dot main dot add scale, and I am going to add a scale of -1 and x, 1 and 1, and then I'm going to call model matrix dot main dot. Okay, now we have another thing that we need to change as well. So we have set shader matrix, but we need this shader matrix pointer. We don't have that. So what we'd like to do now is to say we're going to change model matrix a bit more and say, rather than everyone setting the shader matrix pointer needing access to that to put it in, instead we're going to say we're going to store that inside the matrix, so it just knows its shader matrix pointer. If we want to change that, we can change that at any time, but the matrix keeps track of that, meaning that once it's set, so we are going to change these functions which are actually on. Why is this happening? Make it stop. Okay, which is actually on matrix. So on matrix, rather than having set shader matrix here, we're going to make two functions. One of them is set shader matrix that takes in a matrix pointer, and then we need, it's an int right, int shader matrix pointer, so we'll just keep track of that inside our matrix. Okay, so int shader matrix pointer, doesn't matter what it is to begin with. If set is called with this, we can say this dot shader matrix pointer equals shader matrix pointer, and then we also set it. The other function will simply not take anything and use the global or the class variable shader matrix pointer. So in that case, we don't have to change the code we already did if it's sending in the shader matrix pointer. We don't really need it everywhere, but anytime it's called with it, it'll just restore the variable. We can fix that and clean that up later. For now, we know that Spaceship can call this set shader matrix, adding the scale, and then drawing the plot again. So okay, that's our base Spaceship here. Okay, we need something more interesting. So let's start by saying, before we do the other thing, we're going to lengthen this a little bit. 1.7f for both of them. See how that looks. Okay, that was only added to, yeah, okay, forgot to actually set that. Okay, base Spaceship there. Now I can load stuff onto it. I haven't really designed a spaceship exactly in this way, but so if we do something like circle graphic dot draw solid circle, how does that look? Kind of big. So okay, we want to kind of revert to a matrix size that we can handle better. So does anyone remember what we call here if I want to get back to where I was at the beginning? Can I call load identity on the main? So whatever calls this Spaceship's display function, it has set up its world in a certain way. For instance, in our case, it's already sized it by 5 to draw the spaceship. Maybe it's actually putting the spaceship within a world within its world. So it's already made transformations on its main transformation matrix. So can we do load identity to that? Because what we want to do is that when the display function for the spaceship ends, we want the main transformation function to remain exactly as it was when it was called, so that whoever called it can trust that their transformation is unchanged. So we change it, but we need to be able to revert it. So we have model matrix. We implemented this last week. .main dot matrix dot main dot push matrix. And what push matrix does is it takes the matrix as it is right now, and it simply stores it on a stack. And then we keep on editing it, and when we call pop, we get that version of it back. So what we would always do is either inside every display function or around every display function that we call. It doesn't matter which is, just make sure we would call push and pop. What we're interested in right now, though, is to push the matrix here, and pop it again after we've added these scales and stuff. Here, we'd like to pop it again. Just make sure there are an equal amount of pushes and pops within our. Let's take this one out for now. So now we're going to draw a solid circle. It'll still be a bit too big, I imagine. And I'm always forgetting this part here. Okay, so there we have the circle, but it's too big. So we need to do model matrix dot main dot set add scale, something like 0.5, 0.5, and Z doesn't matter. Okay, so that's our circle there. I don't know, is this a good enough spaceship, or do we want like little boxes on the sides? Fine for now. Now let's add a little bit of something to it, just to use the translations a bit as well. So we've scaled it down there. Let's say we add a push and a pop outside of that, like so. Then let's push matrix, and before we scale, let's do a translation. Add translation, and in the translation I'm going to translate 1 to the right and nothing on Y and Z. Then I'm going to draw a solid, it'll be rectangle, graphic dot draw solid square. Okay, let's have the scale here, scaling the x to like 0.2, the y to 2.0. See how this looks. Okay, so there we have. Okay, let's not translate it just so far. Let's say minus 0.8. Okay, so this should look nice, and then we'll just do another one. Another one the same, except we translate to 0.8 instead of minus 0.8. Okay, so nice little spaceship. Now finally, okay, so this is just an exercise in kind of taking these forms and sending them all over the place. The interesting part is when we start moving this around, we can just affect one matrix and trust that all the transformations that this adds onto that matrix will happen within the coordinate frame that we're working with. So if we say draw the spaceship here oriented like this, none of the other transformations have to change. That will be one transformation before, all the other transformations will fall on top of that. So I'm going to find one more thing here. This one here. Aha. So the color location is something that we kind of need to know about as well. Okay, that's one more thing. If we go to Spaceship, that we need some kind of access to here. If we want to say, let's have the color of the first stuff, the base stuff, we can have it just black. The color of the sphere or the circle, so that's just bright red. On the sides we can have bright blue. Okay, what we need here is the color location. For now, I'm gonna say we can take here int. I know this is kind of a hack here, but display. If we have time, we can fix this as well. You can tidy this up and make sure that the color location is also accessible in some way. So okay, now our spaceship has different colors as well. Okay, then we could add a little triangle graphic and put that up front and stuff. We'll do that if we have time. For now though, the main thing that we need to do is to say, okay, now we can draw this spaceship. And if we can come here and say public spaceship position dot x equals 10, position dot y equals 30. Okay, this doesn't change a thing, except what we need to do before we do anything else in the display function is to say matrix dot main dot push matrix. Then we add one translation. Translation that is translating the entire thing. Draw everything, and then finally, in the end, add a single pop matrix. And so into this translation we need to say position.x and position.y. And okay, so now, whoa. Aha. Position is new point 3D. Well, okay. So one thing we want to do here. Does anyone know why it went off the screen? Can you tell me? Does anyone remember what I did in the beginning? Yeah, I have this scale here. So going to the correct location really has to happen before this happens. So let's put this into the spaceship display itself. But this is simply going to affect the entire thing. So we go to the correct position, then we scale the spaceship. What we could also do is add scaling within all of the small subroutines here just to make it different, but this is good enough. So this ought to... Okay. So now let's change the location. But what we really want is to be able to see it dynamically changing location, changing the orientation. So what I'm going to do here next, or well, what would be a nice type of data to add at this point? So what does this spaceship need? Okay, it needs some kind of rotation. So we can say float rotation, and we can go in here and say rotation equals 30 degrees. And then after we translate to here, we can say model matrix dot main dot add rotation z by 30 degrees. No, sorry, by rotation. Okay, so it's now rotated by 30 degrees. So we have this way to statically set up this spaceship in whatever way we want, and the stuff like the position and the rotation, we simply add those transformations first, and then we add whatever transformations happen while we're actually drawing the spaceship itself. But now we actually want a way to move it around, and we want it to kind of constantly move, so that whenever we're doing something, I don't want to just, I can't just say like, I'm in here, where's the update function? Like here, if key pressed, I'm just changing some position by some fixed amount. Even a fixed amount times delta time, I'm still just moving along the y-axis. I really need to move this spaceship in the direction that it's turned. We can start by saying, let's change this here in left and right, and say we're going to call spaceship dot rotate by some amount of degrees. Let's just say 180 times delta time. Okay, but we don't have any rotate function. So inside spaceship, we're going to need that. Let's just stick it in here. Public way to rotate. But is this really what we want? So yes, we'll take a float rotate rotation, and then say rotation. No, okay, let's not call it rotation. Let's call it just rot2 or rot add. So rotation plus equals add, and then we can go into the game class again. Okay, wait, how is rotate? Takes a float, public. Okay, fine. That should work. Now I should be able to say when I'm pushing right, I should go minus the same amount of degrees. So spaceship 1. Okay. Alright. So pushing the buttons, I'm rotating the ship. That's fine, but I just have this rotation number. If I now want to push a button and make sure the spaceship moves forward, how can I do that? Okay, let's even imagine that instead of doing this, I'm actually going to grab this code here and say spaceship 1.update. Delta time. And inside spaceship, so I'm going to make spaceship a bit more generic, or it doesn't simply, well, it controls its own input in a way. The best way here, though, would be, okay, so update, float delta time. I'm going to stick this code in here. And now we don't even need spaceship 1. Just rotation minus equals this. Okay, so we don't really need. An even nicer way to do this would actually be to have some kind of keyboard set, just booleans on the spaceship. So there's one part of our program that controls all input, and it simply says, okay, this button is pushed, then you should be rotating right, be rotating left, but not actually do the rotation there, but allow the update function of each object to update its own stuff. So nothing is updated outside that. So we call update. In this case, we're just going to use the GDX input as this variable, because that's what GDX is doing. Whenever it gets a keyboard event, it grabs that event and sets these constants here, or sets variables behind these constants, so that any time we call is key pressed with the same input twice in the same frame, we're always going to get the same value. It's not actually checking what's happening now, it's checking how is it this frame, but between the frames libgdx is checking for pushes and releases. Anyway, so we have this here, and this should work the same way. Okay, there it is, and it rotates, fine. Except now it's controlling all of its own stuff. Inside the update function, we're just calling spaceship.update with delta time, the current frame time. Inside display, we're just calling spaceship.display. So spaceship knows its own display routines, and it knows its own update routines. My question now is, if I go into spaceship update and I steal some code from here, from this update function, let's take the rest of this keyboard input. Okay, I'm not really interested in what happens if I press down. You can worry about slowing down later on. What I'm interested in at this point is, what do I do here? If I press up, I want the spaceship to move forward. And I want it to move forward the way it's oriented at this moment. Come on. Okay, so right now, if I press down, I want the spaceship to move in this direction. How can I make that happen?
translate through y-axis?
Translate through its own y-axis.
Yeah.
Yes, but the only information I have about its own y-axis is this rotation number here. So what I'd need to do, I'd need to say, okay, this rotation is an angle. I need to take the cosine and the sine of that angle, and that will give me a vector which I have to travel along. And this is actually possible. But what would be more interesting, actually, do you get how that would be one way to do it? You can actually say math.cos, and now let's do this correctly, rotation times math.pi divided by 180 degrees. I'm doing this in the right direction now, right? Okay, and I can say this is the x part of a vector that is rotated in the way that my rotation is rotated. Except we're saying 0 is looking straight up, right? So 0 is actually a y-axis. So we have to offset this by 90 degrees. Does that make sense? So instead of cosine being the x value, the cosine is the y value and the sine is the negative x value. Okay, fair enough. We can, you know, if we think this well enough through, then that's fine. So then we can say position.x minus equals the sine times some kind of speed times delta time times some speed variable. Let's just say, well, we can start with saying just times 1. Then we can update that speed later. And then we go ahead and say position y plus equals the cosine. Okay, again, this is one way to do this. And I think it should work. But what I'm looking for is different. Okay, let's see. Okay, ridiculously slow, but it's happening. So okay, our speed should be like, what, 5 times that. Okay, turning, moving. Okay, so it's more like a tank than a spaceship now, though. Let's make this faster. Okay, but it moves still. It moves like a tank, really, because I'm just rotating it on the spot. So we need acceleration and fun stuff with the spaceship. But before we do that, I'm looking for how can we keep track of the spaceship's position and orientation in a more interesting way. Let's take a break now for like 5 minutes-ish. You can think about that while you're at it. Just using the stuff that we've already implemented. Not the OpenGL stuff, but the stuff we've implemented. How do we have a more fun and even a more meaningful way to keep track of the position and orientation of something than this rotation variable and this position point? All right, let's just continue this now. So we kind of talked about this during the break, but is there anyone here who understands what I was getting at about a more meaningful way to keep track of the position and orientation than just setting up these position and rotation variables? A way that will also make it in many ways a bit easier to add the transformations for where the spaceship is and what it's doing later on.
I'm still not entirely sure how you're doing the forward movement.
Okay, let's go through the forward movement now. This is basically, I don't know, we can have something like one note. Just to draw something here into the video. Okay, fine. Let's check that out. Okay, so the idea here is that if we have a unit circle, that really great unit circle, the only thing I have now is a rotation in degrees. So imagine we have a 30-degree angle. That means if the x-axis was forward, that is, if this was forward, this would be the offset, and I'd want to move in this direction. So this point here, which is cosine of the angle that I'm working with, that would give me the coordinates for a vector in the correct direction. However, we were imagining y as the forward direction in what we were working with. So we have a 30-degree offset, or an angle degree offset from y instead. So this would be the point that gives us the direction we should be moving in. And this point is minus sine cos, right? So it's just a kind of 90-degree rotation onto the original rotation. So minus sine for the x, cos for the y. So go back to the program. We have minus sine for the x, cos for the y, but that's the vector. We can't just put the position to that, we have to add that to the position. So we're actually adding the position to that here. Oh no, we're adding that vector, sorry, to the position, not the other way around. We're adding the sinus, because the sinus uses radians, but rotation is in degrees, we have to do this stuff. Then I'm multiplying with delta time, and 15 is my speed per second. So that's how many units I'll travel per second is 15, whereas delta time is the fraction of a second that this frame should be updating with. Okay, so now the rotation happens and the forward movement is added to that. So each frame I'm adding delta time times 15 in that direction. So we're basically building a vector that has this direction and only these parts without the delta time and 15 would be a unit vector. X and y being sine and cos, that's a unit vector. Times 15 makes it a vector of the length exactly 15 in the same direction. Times delta time gives us the fraction that we should move inside this frame. So that's the idea of actually doing the motion. Is everyone cool with that? I'm wondering if we should just stick to that rather than complicate things, or if you're cool with putting it up in a different way. So this is fine. This is a good way to do this, in fact, especially if you have a simple game, and the game that we have now is just this ball that's moving around. The thing I was wondering, rather than doing it like this, would be actually keeping track of a position, a direction vector. A vector that tells us in which direction our spaceship is facing. And not only could we keep track of that vector, we could keep track of an entire coordinate frame. We can use a matrix, use one of the model matrix, just an instance of the model matrix class, a specific instance for our class. We could add these rotations and these translations to that, just using the functions that we've already built into model matrix. Let's set that up. And then finally, when we draw, we don't even have to do add translation and add rotation. Instead, we can simply add the transformation of our spaceship matrix to the main matrix. Does this make sense? Should we do this? Let's do this then. Okay, so what we're going to do is, instead of a position and a rotation, we're going to say we're going to make a model matrix, and we're just going to call it I'm wondering if we should just call it M. What's a good name? Matrix. Orientation matrix. It's both a position. Okay. position and orientation. No, that's not good. Matrix orientation. Okay, so it's the position and it's the orientation. Alright, so now instead of this, should be able to say orientation equals new model matrix. Then if we wanted to start out in the same position as we did before, we can do this again. We can do orientation dot add translation by 10, 30, and 0. Then we can do orientation dot add rotation z 30 degrees. Inside the update, instead of doing this, you can say orientation dot add rotation z. Use the same number here. Is this making sense? Alright. And minus for when we press right. Okay. So let's skip the up part and see if we've actually managed. No, there are more things here. Now, instead of this, we should be able to do model matrix dot main dot add transformation. Okay. At this point, we go into the matrix class here, not model matrix, but the matrix class itself. We take this function here, add transformation, that takes a float array, and we duplicate that, we copy that into another that takes a float buffer, and then it does exactly the same thing, except rather than calling the matrix with the brackets, it calls the float buffer with the same name with get. Otherwise the exact same function. So we go into Spaceship, and rather than doing it like this, we simply send
words to live by. I'm hoping this just works now.
like so. So we get the matrix. Add transformation, orientation dot matrix is here. Okay. All right, what are we doing wrong? Okay, model matrix here, rotation dot load identity matrix in the beginning. Any pointers here? So we're adding the translation and the rotation. That worked. Okay, we're not really adding anything else. Then we add the entire transformation to main. We push that here. We pop it on the end, so it shouldn't be constantly adding. Okay, there it is. And the rotation works. Okay. Whew. So we're going to manage to at least finish this. Anyway, now we're using the matrix, and this is actually going to help us later on. So bear with me, and we have the same functionality as we did before, but this is in the end going to be of some help. So let's go back to Spaceship, and now the question is, what do we do about this? So what I want to do with model matrix is I want to be able to get from it its orientation, or its vectors. But since we don't have a vector class yet, I think it's high time to make that now. Okay, so we're going to make the class vector 3D. We're going to start the same thing as the points x, y, z. We're going to add some functionality here. We can say public vector x float y float z. This, yeah, vector 3D. Okay, we might add functions here like dot product and stuff like that later on, but let's see how we can work with this now. So what I'm going to do on the model matrix is I'm going to say I'm going to make a couple of get functions here. Public vector 3D get A. Okay, so A, the A vector of a coordinate frame is simply kind of the transformed x axis. So get A would be the same as kind of getting its x vector or its x axis. So get A would be return new vector 3D, and we remember that the matrix itself is lined up so that values 0, 1, 2, and 3 are actually a vector. Then we have 4, 5, 6, and 7. 8, 9, 10, and 11, and then finally we have the point. So we can get the point of origin as well. So we get 0, 0, 1, and 2 is enough. We know it's a vector. The 0 in the end would be make it homogeneous coordinates. Okay, so we can get A. We do get B, take the next vector, which is get at the positions 4, 5, 6, get C, which is 8, 9, and 10, and finally we can get origin, which gives us the point of origin, which would return not a vector, but a new point 3D. With 12, 13, and 14. And then we need this function here into our point 3D as well. But also another one. Nothing here. 0, 0, 0. Yeah, okay. Obviously, like so. Okay, so model matrix now has these functions. Let's save everything. Why is this? Yeah, like so. Okay, so now we have ways to get these base vectors of the coordinate frame we're working with out of our transformation matrix. So we have a transformation matrix, and we say add rotation, add transformation, add translation, add scale, do all of these things to it, and at any time we can say, okay, I know you represent a coordinate frame, so I just want one of those vectors. In the 2D case now, we're going to say the y vector is kind of our forward direction. When we go into 3 dimensions, usually the forward direction would either be the z-axis or the negative z-axis. In our cases, it's usually going to be the negative z-axis. Because if we look at a 3-dimensional coordinate frame like this, with one sticking out of the board, the direction we're facing is inward along the negative z-axis. Anyway, in this case, we're going to say this get B will give us our y-axis. So inside our spaceship, we should be able, instead of adding this sinus rotation stuff, that stuff has already been done inside our matrix. So now we should be able to say vector facing equals orientation dot get b, and we can say position well, would we actually say, okay, we could say position dot x, but we've actually wiped that out. So what we want to do is to say instead orientation. Okay. What we actually want to do is to say orientation dot, we're going to use the facing later on. We definitely have the time to do that. Orientation dot add translation, and we can say 0 delta time times 15 and 0. Float, float, float. So, okay, sorry. Now we're translating by the y-axis. So, we move like this. Because obviously every translation that we're doing is happening within, but still we're moving like a tank. So what we'd like to do now is actually to make our spaceship move kind of frictionlessly through the air, right? That would be an interesting thing to do. So now we're more interested in, so how could I do this? What I need to do is I need to kind of keep track of two directions, right? Sorry? Yeah. So I need to keep track of velocity specifically. My velocity is just 15 always now if I hold the button down. As soon as I release the button, my velocity is 0. 15, 0 in any direction. So now we need a vector for velocity. And rather than updating it with speed, we're updating it with acceleration. So vector 3D velocity. And we can just go in here and say velocity equals new vector 3D 0. Okay. Wow, can't seem to do capital letters right. Okay. So I have a velocity vector. So what I want now is somehow to add to that velocity vector. So rather than actually just translating the actual spaceship by its own y-axis, right? I instead want to say so this is where I'm facing. I want to say velocity.x plus equals facing dot x and velocity y plus equals facing y, except I want to do that times delta time, and I want to do that times some kind of acceleration. So 15 is going to be a way too high a number now because this is going to be added constantly. Let's just start with 1.0 and see where that takes us. Okay. But in the end, we actually need to add the velocity, except now we don't want to add the velocity inside is key pressed, because we want, or well, we want to add to the velocity there. We don't want to add the velocity to the position only there. So now we want to do orientation dot okay, now this is going to be tricky. This is actually one transformation that we don't want to add like on top of the transformed matrix that we're working with, right? The velocity is happening in the entire air. So what we need to do in the matrix here is, rather than multiplying it with the new transformation to the right, we actually want to multiply it the other way around. Make sure that you check out the end of the video where we actually add this function here, add translation base chords to the model matrix class, and then inside Spaceship, instead of the hack that follows, we simply call add translation base chords with the velocity times delta time and the velocity y times delta time, making it simpler than actually hacking into specific positions in the model matrix that we're working with. And the same we do in laser blast in the update function there. Orientation dot matrix dot put, yeah. So I'm going to go out on a limb here. We should actually put this inside the matrix function itself and say it's a way to kind of forcefully translate it. But in here we're going to put orientation dot matrix dot get at the position 12 plus velocity dot x times delta time this is a okay, so we need a bit more speed here. So 1 isn't enough. Let's say 4. Hope it won't be way too much. Okay, so wherever I'm turning, I'm adding velocity in that direction, and then I just keep that velocity. If I now turn here, I'll add this velocity. So in order to brake, let's make this much more. I guess 15 wasn't really that far off. Maybe we need it even faster. Okay, so now we have this, my favorite type of controlling a spaceship, where it just floats around. So what we then need, we could actually put it in here, but it's more something that the world should be able to view. Could put in something like, if we go beyond, we'll come in at the other side. Let's not spend time on that right now. So we have the motion that we're looking for, and it's all happening within the update function. The only thing that's kind of a hack here is this. What we would want is to have a little function that does this inside the matrix and call that. But since time always seems to gallop away from us. I'm going to leave it here. The final thing I kind of wanted to do was to see if we could add something like shooting stuff out of a spaceship, which would start with a beginning location relative to the spaceship, but get its own velocity. Should we try to do that in 5 minutes? Or do you feel that that's... Okay. The thing is, what we then need is another class. And this class would be, let's just call it blast. Even laser blast. Okay, and laser blast also needs a position and orientation. And we could actually do that with a matrix as well. So let's just say model matrix orientation, just the same thing as we're doing on the other side. And we're going to need velocity vector as well. We can probably copy a lot of the stuff from Spaceship. So let's just start by copying code here into laser blast. Okay, so we'd like to have this laser blast and I guess we'd like to say, well, I think we just like, oh, never mind. We'll just make these things public here, so that whoever shoots the shot can just access that directly. It might be nicer to do it through functions or do it through the constructor. Okay, so nothing about pressing keys, but at any point, this, however, should happen. So we have the orientation matrix. It should be oriented in the same way as the velocity, but let's leave it the same way as we have it here. When we display, let's just say we want one of these little guys here, a bit smaller, push, pop. We don't really need anything else since we're just going to draw this one thing. Okay, let's see how that looks. Alright, so the display should just go to where it's oriented, scale it like something. We don't even need this translation. We just need to scale it like this, draw the solid square, and it should look like a... And actually, let's make it a different color. So laser blast, and we'll put a color here, yellow. Right. What we need to do now is we'll just let the spaceship keep a list of laser blasts. Okay, this should come out of our util blasts equals new array list of laser blast. So now we're going to go into the update function and say whenever someone is okay, we have something like key just pressed, right? Is key just pressed? Space. Okay, now we want to do something. Now we actually want to create that. So we'll say laser blast v1, which is blast, equals new laser blast. But now we have to set its velocity and its orientation. So blast dot orientation equals new model matrix. Okay, why do we get this? Yeah, laser blast. Okay, orientation is new model matrix. Blast dot orientation equals dot load identity matrix, just to make sure. Okay, what can we do now? Simply to just orient ourselves to the spaceship first, then to the correct location for this particular blast, and then give it a velocity. Blast dot orientation. So we just start with add transformation and use our own orientation, which is the spaceship's orientation. So that way we simply add to it the location of the spaceship. We're there. Now all we need, and why is it complaining, is it dot matrix, like so. Okay, so now we're at where the spaceship is. And then we have an x-axis to the right, so we can simply say, okay, blast dot orientation dot add translation, let's say 0.8 to the side, a little bit forward, I guess, 0.4 or something, and then 0 here. This has to be floating points. Okay, blast dot velocity equals blast dot orientation dot get b. So now we have all this data inside the matrix. We've set the transformation from the matrix to the spaceship, we've moved it a little bit, and then we have data in that. Where are we oriented? Where are we positioned? So if we ever need the position solely, we can always say get origin from the matrix. If we only need the direction of the y-axis, which is what we're getting now, we can simply say get b. A being the x-axis, b, y, c, z. Okay. So we're a bit over time, so those of you who need to leave can do that, but I'm just going to finish this now. Just like last time. Can't really get everything done on time. Okay, so that's the velocity. Then we should be able to say blasts dot add blast. That makes sense? Okay, then I'm going to do the whole thing over again. I'm going to add another one. So okay, now blast is a new laser blast. Now I'm going to go minus 0.8. Okay, and I'm going to add that blast. So now what I need to do is that inside my update function, I need to do for how was this again in Java, like for each yeah, for a laser blast like so. In blasts so we're going to do blast dot update delta time, so all of them will be updated, and then in the display function we do the same thing. After we've drawn all of this and popped it, we're going to go for each blast here, we're going to do blast dot display. It might be a better idea, and I need to send color location in there. It might be a better idea to actually generate the laser blast and send them out to the main program. So the main program can start kind of comparing all the stuff, so the laser blasts aren't hanging onto the spaceship object itself. But in this case, we're going to leave it here. And we're going to see if any of this actually works. Okay, it's going super slow. Okay, so the velocity definitely needs to be more. Actually, I'm going to do one thing to make this cooler. I'm going to say blast orientation get B. And let's say blast.velocity.x plus equals velocity.x. I'm going to add the speed of the ship itself. So it kind of follows the ship, so I don't leave them hanging behind. Okay, but what we need is a bigger translation. So 0.8, this would be 4.0. We're in a bit of a pickle here with the scaling. We added that 5 times scale. So this would be something like 2. Okay, let's try this now, 2.0. But blast velocity, then we can say velocity blast.velocity.x. You can multiply that with, let's say, 10, and same for y, and see how that looks now. Okay, one of them works. Forgot to change the other. Okay, more like 50. And we need to do all this with the other one here. Yes, I'll change the color of the laser. Want it a bit darker. You should actually just change the color of the background, I think. It would be better. This should be a bit darker so we can see it better. Okay, spaceship. Doing this, cool. So you can see, even though I'm moving kind of to the side, if I'm going this direction, the shots look like they're going out of the spaceship itself. Okay, if we had had time, there are certain things I would have done differently here. Okay, so this looks nice. Like this here, I would like, on the vector 3D, I would simply say I'd like to have a function here that's called public void scale. It takes a float sx, float sy, and a float sz. And what it simply does is this. Okay, so that would mean that I can scale this vector, and so inside spaceship, rather than doing this, I should be able to simply say blast.velocity.scale by 50. Well, yeah, actually a vector would usually just be scaled with a single number, so let's just do it like that. Scale, just float s. So, okay. All we're doing here then in Spaceship is we're simply scaling the vector. Let's save everything and see if this. Yeah, 50f. Instead of doing that. And the same, we'd like to be able to add another vector to it. So same, inside vector 3D, we'd like to make a function called public void add, which takes another vector 3D like so, and we simply do x plus equals v2.x for y and for z. And that means rather than doing this here, we could simply say blast.velocity.add our own velocity. So it looks cleaner that way. So I'm adding this here at the end just to clean things up, just like so. Yeah, scale is working now, and that should actually give us the exact same effect. So yeah, I thought I'd have time to make the spaceship look cooler and time to even have the shots like hit a small ball or something, but fair enough. At least we're working with vectors, and this should be a nice kind of base or basic idea for any of these types of 2D games that you're setting up, and just kind of the idea and the way to take something and have it moving in a specific direction and having it updating its own position and its own velocity and its own acceleration inside these update functions. So the main thing to take away from this is the fact that the way we set this up, inside the main game's display function, we just call spaceship.display, and spaceship knows how to do its own thing. And inside the main update function, we simply call spaceship.update, and the spaceship knows how not only to check for if it should be rotating right left, but also to update its own velocity with an acceleration and its own orientation, update its own orientation, and make sure that everything is set up in a way that when the display function is called, it can simply access these things. It can access the matrices, it can access the positions, and it can access the vectors and the colors, and simply draw what the update function sets up. So the update function uses dynamics to set up the position and the orientation. The display function takes that static position and orientation and draws it in a meaningful way. Okay, I'd just like to add some cleanups here at the end. Things that we did that were maybe not perfectly as we'd like them. So if we go into Spaceship here, where we're updating, especially here, we're updating the position using the velocity vector, and we actually want to update kind of the position in the base coordinate system here. Whereas usually when we're doing transformations, we're adding them to the transformation matrix, and we're using the transformation matrix itself, its point of origin and its vectors. So this is kind of a hack here, going into the matrix, getting number 12 and number 13. This is not something that we should see inside the Spaceship class. So instead of this, it would be nice to go into the model matrix, and here where we have add translation, we can make another function, public void add translation base coordinates. So I'm just going to put that in there. And then instead of actually using the vectors themselves as we're doing here, we're simply going to add tx plus what was originally in number 12. The same thing that we're actually doing here in Spaceship. So we're putting into 12 its own matrix number 12 plus whatever we're going to send in there, plus the translation, whatever's added. So inside model matrix, we have what's already in 12. We can do it the other way around just so it's clear, plus tx. And we can get rid of the rest and say we add ty tz to the y and z coordinates of the point of origin respectively. So this is the first, second, and third number in the final column, in the fourth column of the transformation matrix, which is the point of origin. So add translation base coordinates, and then I'm going to see if we can't just simply use that instead. Say orientation dot add translation base coordinates. Here we're going to add this, the x coordinates, this, the y coordinates, and 0 for the z coordinates, so we're still working in 2 dimensions here. We're going to see if this doesn't simply give us the same functionality as we had before. Okay, it does in the Spaceship, and we can do the same in Laser Blast. The update function, simply do exactly the same. This. So we're not hacking into specific locations in the model matrix here. Let's see that work. Okay, it works for the Spaceship itself. It's adding the velocity constantly, and it works for the laser blasts. Okay. One thing about the laser blasts as well, obviously we would want to do something like having a lifetime on them, adding some kind of function and saying lifetime plus equals delta time every single frame, and then something like if lifetime is bigger than max life, or some specific number like 10 seconds, or just if it's off the screen, some way of deciding that a shot shouldn't be there anymore, then dead equals something like dead equals true, and then have some way, like this would be a class variable dead, and have some way for the Spaceship itself then in its update function somewhere like here for blasts, laser blasts update, and then if blast dot dead, blasts dot remove blast. A way, because in the current way we're implementing this, these shots, even after they go entirely off the screen, we know that these shots are going to be still updating themselves to infinity, and they're just adding and adding and adding to the list. And then you can figure out yourselves for a type of list. This type of list, is an array list a good collection to be using, or is it better to be using something else?